This is the second part of the screencast on Divide, Conquer, Glue in BuggleWorld. In the last screencast, we saw these designs, and we saw how they could be made by a nested boxes method, whose contract we examined, and then we used the nested boxes method to make two different kinds of designs. And what we're going to do now is we're going to flesh out the implementation of the nested boxes method. But before we do that, we're going to do some more wishful thinking, because as part of Divide, Conquer, and Glue, even as we implement some methods, we'd use wishful thinking with other methods. So let's assume that we have two other methods. The first is a box method. The box method is something that's going to take a parameter n, which specifies a side length of a box and a color C, and then we'll draw a box of that side length and that color in the way that the buggle is facing. And this is very much like the doghouse, build doghouse method that we saw for puppy buggles. So that's one such method that we will assume exists. And here's another method that we're going to assume exists. It's called the jump method. And the jump method is something that takes two parameters. It takes an amount forward and an amount left, and it causes the buggle to change its position, but not its orientation or its when going to this new position. So for instance, if we imagine that our buggle starts in the center of this grid here, then jumping up 2 and to the left 1 leaves it in this position, jumping forward by 1 but left by -2 moves it to the right to this position, jumping -1 is backward, and then by 2 brings it to this position, and jumping by -2, 0 brings it to this position over here. So in each case, the buggle has not changed its orientation. We will assume that although the color or heading of the buggle is not changed, that the buggle will end up with its brush down regardless of what its brush state was to begin with. Okay, so let's say we have now the box method and the jump method. What would happen now to implement nested boxes? So we're returning to our nested boxes method that by wishful thinking we assumed existed earlier. Now we're actually going to make it exist by defining the Java code for it. So what I would like you all to do now is to turn off the screencast and figure out what are the statements that should be in the body of this nested boxes method. And then when you turn it on, we'll talk about the solutions. Welcome back. So here are the solution, or one solution to the nested boxes method. Let's talk about it. So let's assume that we have a buggle that's over here facing in this direction, and it's supposed to be making a bunch of nested boxes that are over here somewhere, like so. First thing we want to do is we want to move it so that its position is here, and that's accomplished by a jump of forward and left. So we're using our forward and left amount here to jump to the correct position. We're then going to call the box method with the outer side and the color C1, which will then make an outer box of color C1. And now we're going to jump 1 unit in each direction to make the second box over here. And then its side length will be outer side -2 because it has 2 less elements on each side. We're then going to jump to make the third box over here. That's another jump of 1, 1. And now we're going to make a side length of outer side -4. And of course the colors are alternating. Our first color is C1, our second color is C2, our third color is C1, our fourth color is C2. And finally, to make our fourth box, we jump 1, 1 again and make something that's outer side 6. Outer side -6 rather. Okay, so now after all of that, we have to make sure that our buggle's position is invariant. So we have to bring it back to this spot. So what we have to do is we have to undo each of the amounts. So we have to undo the amount forward plus a 1 plus a 1 plus a 1. And jump is very nice for this. We just undo all of those by saying -3 minus forward undoes all of those. And to undo the lefts, we have a left plus 1 plus 1 plus 1. We undo those by -3 minus left. So this final jump brings us back to our original position and leaves the position of the buggle invariant. Okay, now let's take a look at the other two methods that we assumed existed. Remember the box method? The box method, again, is like build doghouse. You should take a moment, turn off the screencast, and figure out what the implementation of this method is. And here is the implementation. It's something that's pretty straightforward. The very first thing we do is we set the color of the buggle to be the color we want to draw the box in. And then we're going to repeat 4 times, going forward by n-1 and turning left. And the reason for the n-1 is that there's an off by 1 error if we're not careful with how far the buggle goes forward. And so we just repeat that 4 times, and that's the end of the box method. And lastly, the last piece of our puzzle here is the jump method. So review the contract of the jump method, turn the screencast off, and figure out what the implementation of the jump method is. Okay, welcome back. Here's the implementation of the jump method. What are we going to do? We're going to assume that we bring our brush up so that when we're moving around, it's not drawing everything. We go forward by the forward amount. We then turn left and go left by the left amount, and we now undo the left with a right, so we're facing the original position. And we now put our brush down. Notice that that satisfies the contract that it leaves the brush down. And there we have it. We have now implemented all of the pieces of the nested boxes method, and we did it by wishful thinking, first by assuming nested boxes existed, then by assuming that the box and jump method existed and implemented the nested boxes method in terms of box and jump, and then we implemented the box and jump method. Now, this approach to problem solving is called top-down problem solving. It's called top-down because we start with the problem that we want to solve. And then we break it down into subproblems using the divide, conquer, and glue method. So in this case, we assume that we had a nested boxes method, and then we assume we had smaller methods called box and jump that we could implement nested boxes in terms of, and then we implemented the box and jump methods. Now, when it actually comes to coding these methods, we do not have to code the methods in the top-down approach. So another approach to coding the methods is to do them in what's called a bottom-up fashion. So even after we've done our divide, conquer, and glue and have assumed that we have nested boxes and box and jump, we can in fact first implement the box method and then test it out, and then implement the jump method and then test it out, and then implement the nested boxes method and then test it out, and then implement things like design 1 and design 2. So if we go in that kind of order of our implementation, that is called bottom up, because we are starting at the smallest pieces, we are implementing and testing the small pieces, and then we are going toward the larger pieces. So even though we decompose the problem from top down, we can implement them from bottom up. Now, an advantage of implementing things in a bottom up fashion is that testing is pretty easy. So when we implement the box method, it's pretty easy to test it on a particular buggo. When we implement the jump method, it's easy to test it. And once box and jump are done, it's easy to test nested boxes, and then it's easy to test design. It's not so easy to test in the top-down implementation. Suppose the very first thing we do is we implement design 1 in terms of nested boxes, as we did in this approach. Then it's very hard to test because we haven't implemented nested boxes yet. So how do we decide if nested boxes is actually working? So in practice, if you're trying to develop things in a top-down fashion, you need what are called stub implementations, which are little pieces of code that don't actually do what the method is supposed to do, but do something that approximates it. So for instance, something that the nested boxes method could do is it could paint a single cell that's in the left corner of the nested boxes to show that it's doing something, and then later on you could flesh it out so that it does something more. And this brings us to another point, which is regardless of whether you're doing bottom-up or top-down coding, regardless of whether you're doing bottom-up or top-down coding, you should always use an incremental coding style. And incremental coding says every time that you add a statement, don't try and solve everything at once. Just do something simple. Do something simple and test that. So for instance, when you're off writing the box method, rather than drawing all 4 lines of the box, first just draw 1 line and make sure and test to make sure it draws the 1 line where you expect it to. And then when it draws 1 line, then draw the 2nd line, and then maybe add some other lines, such as the 3rd and 4th line. When you're drawing the nested boxes, don't draw all 4 nested boxes. Have it draw 1 box first. Test that out. Make sure it works. Then you can add other boxes. And then when you're doing something like design, don't have it draw the entire design. Have it draw just one of the boxes, and then add the other boxes later. So this is called incremental coding. It says you don't solve everything at once. You add 1 statement at a time, and you test it to make sure it's doing what you want. And then you know that you're making progress as you go along the way. Okay. We're going to conclude now by talking about a slightly different contract for the nested boxes method. So this is different than the contract we looked at earlier, and it differs in the following spot. So before we said that it would leave the buggles brushed down and it would change the color of the buggle to be color C2. And it turns out that that was easy because in the particular way that we implemented it, the last thing that we drew was in color C2, which left the color buggle with color C2, and we did a jump, and a jump leaves the buggles brushed down, and so that was convenient to specify. But in fact, in almost all cases, what we really want is we want as many properties of the buggle to be as invariant as possible. So we would like the color and the brush state to be invariant when we call nested boxes. That is, the color and brush state of a buggle after nested boxes is called should be the same as the color and brush state before nested boxes was called. And if we do that, then there's less that we have to worry about changing along the way. It's a lot easier to reason about gluing together nested boxes with other kinds of methods if these elements of the buggle are not changing. So it turns out if we make that change in the contract, we can easily make the change in the implementation. And here's the little trick you need to do to make such a change in the implementation. So we're going to assume here that we have the same code as before. So this box here refers to all the same code that we had before in the nested boxes method. And what we're going to do is we're just going to wrap the same code as before with a few extra statements that are going to implement the extra invariance. And all we do is we have these 2 statements up here that simply remember what the original color is by using the getColor method, and remember what the original brush is by using the isBrushDown method. And we store those values into variables. So variables are just places that remember things. And so we can use these variables in the execution frame to remember what the original color and the original brush state are. And then at the very end of our method, before we return, we can set our brush down state to be the same as our original brush state, and we can set our color to be the same as the original color. So what we've done is up here we have saved all the information, and down here we restore that information before we return, and that's a really nice pattern for making sure that our buggle properties remain invariant. So this is a nice thing to use in your code, and it'll be very useful to you throughout the rest of the semester. So that's the conclusion of our divide, conquer, and glue slides. So what did we learn here that was important? Well, the number one thing we learned that was important is that it's really important to choose abstractions suggested by divide, conquer, and glue. We use wishful thinking. And then we break our big problems into smaller problems, dividing them. And then the glue is how we glue together the method calls to do the right thing. We also learned that divide, conquer, glue is a top-down process where we start with the problem that we want to solve and break it into smaller problems. But then when we actually do our coding in Java, we have a choice of whether to do that coding in a top-down, bottom-up, a top-down way, a bottom-up way, or some combination of them. And in fact, it turns out that for coding, that bottom-up is often better because it allows us to test our things better. So this is much nicer for testing. So even though we break down our problems in a top-down way, coding them in a bottom-up way is good. And the last thing I would like to emphasize is that Buggle methods are more flexible when they are invariant. They leave the state of the Buggle invariant in as many state properties as possible, our state properties being position, heading, color, and brush state. So as a general rule, we would like to make these properties invariant across most methods, and that is going to aid the glue process when we glued our Buggle methods together. And that concludes our mini lecture on divide, conquer, and glue.